Yeah, so hi everyone. Hope you see some familiar people from our Discord presentation. So today I will explain you a bit about zk sharding and shard apps architecture. So first of all, let's start from sharding because I noted that the Ethereum community sometimes misunderstands sharding from Ethereum and sharding from general database systems. And first of all, I would like to explain that sharding from database management systems sometimes refer to the idea of splitting some data, or in our case, splitting the networks. So if you have a single blockchain, this is just a single chain network. But sharding means that you can have multiple chains that running in parallel, but they share same execution environment. So like on the picture, you can see that we have several shards that are absolutely different networks. They have in common main shard used for synchronization, and they operate in parallel. So they have their own state, they have their own execution pipeline, but at the same time, they stay as a single chain. And later I'll explain what does it mean. So, but first of all, let's understand why zk sharding and in general, why do we need this idea of sharding when you split your network into subchains. So first of all, you reduce the fragmentation of liquidity from L1. Imagine that you have a lot of networks like Arbitrum, Optimism, zkSync. They all have their own liquidity. So people bring money to these networks. But when you go to the decentralized network based on, for example, proof of stake, liquidity in most of the cases means security. So when you split this liquidity between these chains, you potentially make them weaker to the attacks. So with sharding, you lack of this disadvantage because you don't have this fragmentation. A common liquidity is shared between all chains, but they stay as a single environment, and all this money is in a single environment. Also, you have seamless execution environment, what I mentioned. What does that mean? If you want to make communication between zkSync and Arbitrum, it will require you utilizing bridges, and it's not very cheap. It's quite long time, and in general, not very convenient. You cannot build so easily cross-chain application. So it's not as easy. You can have a look, for example, for cross-network lendings. It's not quite easy. While for sharding, when your cross-shard communication is built into the protocol, your seamless execution environment is quite strength. And also unlimited scaling. In general, you can add as many chains as you would like to, because you don't have any physical limitations other than building L2. For example, like adding another L2 to Ethereum, it will end up to some time when, like, for example, your basic fees exceed the price that you can pay on this L2. So for the key sharding, it's not a problem because it's like a single chain, as I already mentioned. So if we go to bird's eye view of the overall schema, you'll start from some PBS. PBS is also known as proposal builder separation. This is a special kind of sequence that allows you to split builders, people who can build your bundles. Bundles is just a set of transactions. And proposers, people who validate these transactions and propose new block. So they quite interesting utilization in zk sharding that PBS is built with L1 and L2. So we have our own builders and proposals, while we can also have builders from the L1 because compatibility with Ethereum transactions. And in general, this is very beneficial for builders and searchers from L1 because their utilization rate for that they use with Ethereum is quite limited because Ethereum is not quite a fast network as far as you know. So they have a lot of expertise and not utilized, let's say, power. So that can be used on L2 and for our network. And in general, every single shard has its own memory pool and its own set of transactions dedicated to this pool. So if you would like to send a transaction, you send a transaction to a specific shard, so to a specific pool. But these shards has communication between each other using cross-shard communication, and also submit their latest state to a main shard where it has own prover network for the key proof or state transition the key proof, and also the transactions goes through Ethereum as part of data availability and state transition proof correctness of main shard. So we go to sharding, and as I already mentioned, sharding is just splitting data into pods, but it's also can be noticed that you split your processing to a semi-independent subset of peers. In general, for that reason, we have a single validator set between all shards, but each shard has its own subset of validators that's defined after so-called rotation event. So after some rotation, subset of validators chosen and dedicated to a specific shard. And leading this idea, in general, you can have parallel execution, parallel states, but they are binded in common, and your computation go in parallel, but it goes like pure parallel. So it's not like in Solana, you can have true parallelization because your states are not intersect and parallel, but at the same time, you have a global, let's call it global state in main shard called consensus shard. So what is the benefit of our rollup centric approach that's now used on Ethereum? So as was already mentioned, this is horizontal scalability and lack of fragmentation of liquidity. This is first major benefit. Also, as was said, single application and consensus layer between these shards. So it's not like, let's take a bunch of existing solutions, existing L2 networks, and find a way to unite them on some execution layer. No, it's more deep on protocol level. So you have even common consensus layer. It's like two levels of consensus that will be mentioned later, but it's also on protocol level stuff. Also low cost and high speed of transactions. Yeah, low cost is dependent on the specific shard you're working on, but in most of the cases, by simple mathematical proofs, you can show that your transaction costs will be quite spread around the shards. So you, at any time, you will not suffer from high transaction costs because even if the load is too high, new network, like new chain can be introduced, and part of the load will be distributed to a newly raised chain. And also multiple finalization levels. So it's like the idea when you can have not just a soft and hard finalization, but finalization on L2, several levels of finalization on L2. So like, for example, when you send state transition proof to a consensus shard, this is one finalization. For example, you proved on L2 that your state transition is correct and your state can be used on other shards, while at the same time you can have a classic finalization on L1 when consensus shard sends state transition proof to L1. So you can find the proper finalizations that you would like to use and you consider reliable one for your needs. So I mentioned about two types of consensus used. First of all, it's called local consensus, and it's quite straightforward. It's one used on a single chain, on a single shard. So each shard is a decentralized network, and it has its own consensus. So it's quite straightforward by some hot stuff. It's classic one PBFT model, so nothing specific, but the pipeline is quite simple, nothing very difficult. So just for those who know, it's just a current view selection, leader election, commitment proposition block. And after that, you vote for the proposed block and replicate the data after every committee voted for this block. And also global consensus or global state synchronization also. So when every block, every shard has to send its latest state to a consensus shard. So it's used for several reasons. You can imagine that when you have a lot of networks running in parallel and you want to send a message to some other chain, you have to know the latest state of the chain. For example, you want to send money and you want to know what is the latest state for the ERC20 contract state of this account. So to understand this, you can take the latest state from the consensus shard that was sent previously by this target shard, and understand, okay, I know this state was the latest one. They can be already a few blocks ahead, but you care only on the proven one. So that you consider already saved, already correct, and proved with CK proof. And this consensus shard also has confirmation, as both mentioned, auto-soft finalization. And also it's used for address resolution. So what does it mean? Imagine that you would like to send money to some contract and you have no idea about which shard this contract located. So for that reason, the transaction goes, or special request goes to the consensus shard, where it's like mapping address to shard. So like you have some address, you understand what is the shard ID for this address, and send transaction there. So this is quite simple for this consensus shard. And global state synchronization works as on the diagram on your screen. So first of all, each shard sends transactions to some block M, let's say, for time k. So you can imagine time k. And you can see on the screen, I'm not sure, can you see my mouse? Probably. This is update state root for some time k. And here for transaction 2, so for shard 2, also some transaction k. Yeah, in general, it differs, but we say the same, like k here and k time here. So in practice, that will be different time. And you have also state proof for some block that happen to be k minus 10. So that means that you prove the state that was sent to consensus shard 10 T ago, let's say like 10 seconds ago, we consider that. We have each block 1 second. So at the time T will be sent a proof for the block T minus 10. Yeah, because proof generation is quite complicated task. First, complicated because of time and because the computations are very hard. So it's quite unrealistic to send a proof at the same time when you have your latest state root. So you send your proof like for the block before. And in general, it goes like that. So you have k, you send a proof for k minus 10. And for example, other shards can consider it like block k minus 10 is finalized on L2. And we can consider that it's through finalized. But if I want, for some reason, latest state in general submitted to consensus shard, you can use also this one. Yeah, it can be used for some applications that maybe not require so strict finalization. Maybe, I don't know, something not related to money. Yeah, and you can see like after n blocks, you will have the proof for block K that was submitted 10T ago. So quite simple. And what about sequencing? So sequencing is the part of every decentralized network that tells you, okay, how you process your transactions. So how you work with them. And as was already mentioned, we utilize PBS model. And for the PBS model in general, we also allow L1 network to handle L2 transactions. And it benefits us because, first of all, we have more decentralized and reliable searcher builder network. And also we have some sort of competition between native builders and searchers and from builders and searchers from L1. That in general will benefit the protocol. And it also introduces aliveness. So at any point of time, we can be pretty sure that our model works. And yeah, we also have additional network support. And this is how sequencing schema works on a high level. So in general, as was said, mempool actually shared. It's not actually shared. That means that L1 searchers and builders just have access to the mempool of sharding to the shards, yeah, and they just select transactions for searchers and builders and build the blocks and send to relayers on L2, while proposers are only ours, so we don't share proposers with L1. Yeah, because definitely it's quite impossible for the sharded system. And let's talk about data availability. So data availability refers to a few concepts. First of all, the concept of sending data to Ethereum needed or sufficient to prove the correctness of your state on L2. And sometimes it also refers to the idea of rebuilding your L2 state from L1 submitted transactions. So in general, it's consists of two possible solutions. First of all, this is sending a compressed transactions from L2 to L1. So you can just re-execute L2 transactions and get back your state of L2. Or second option is sending state diffs. So you send to L1 state diff between some time t and let's say t minus k. So in general, second option is considered more efficient because especially for the networks with high load, yeah, because your accounts are quite limited. So you have quite limited accounts, number of accounts and storage cells, whilst transactions may be a lot. And let's say you have trading for one account. So you change your balance 1,000 times. You have 1,000 transactions, but at the same time, you just change a single cell, like a single memory cell. So it's more efficient for such high-load system. So state diff submitted as call data. Now it's blocks to L1. So we will utilize new EIP 4844. But for the proofs that is submitted to L1, they will be submitted as call data. It's part of call data on the L1 transaction. And verification will happen on L1 using classic ZK proofs, so state transition proof. And yeah, so these commitments are stored in L1 as a chain. So what that means, so you can restore from these state diffs your any chain that you submitted to L1. So you can go like chain by step by step, like from the end to the beginning, and restore the whole state of your L2 at any time. And simple example of such a preservation storage is quite classic, like signature period, plus data as a key proof and verification cost. Yeah. And this is just the quick idea of state if. Yeah, just to everyone understand, this is a simple picture that shows like if you have some state at time n and at time n plus 1, you can see that at time n plus 1, you have some red state root. So you will have finally it at the top of your tree. So it will be not changed. So you like replaced your state n root with state n plus 1. So that means what I mentioned regarding this replacement with high load. So if you have like, let's say, most left corner cell, red cell, if you just have a lot of transactions that change a single cell, memory cell, it will be more efficient to store your state diffs because you will only keep only sends the latest state of this cell, and that's all. You're not cared about states before, only the latest one. So, and let's talk about this cost. So we're interested about the cost of data availability. In general, target of zk sharding is 60,000 TPS, 1 block per second, and we consider that we have 6 blocks state diff. That means like you take state diff between state n and state n plus 6. And your Merkle state trie depth is just average 3. Yeah, it's quite can be easily shown that the possibility to have something worse is just less than 1%. And using just simple calculations, you will receive that with this price 2,900, you will have data availability transaction cost $53. It's not including actually proof verification and proof. And considering like 6 blocks diff, that will have a additional price for 2 transactions from data availability, just very miserable, like 14 times 10 power minus 5. It's too low price, but you should keep in mind that this is just additional price for data availability. This is not final cost, but in general, such an idea will keep very low price for data availability. And in general, some researchers show that data availability cost for L2 have like 50 to 80% of the L2 cost. So you have to understand that in general, data availability price is like major part of your L2 transaction cost. Okay, so let's talk about how we build applications on such system. As you already noticed, this is not a classic single chain blockchain like Arbitrum or Ethereum. This is a bit more complicated system. And first of all, I would like to mention that in general, development experience will quite likely similar to what you have now, like compatibility with Debian, so you will have a Solidity language, Hardhat, and any other tools that you're familiar with, MetaMask or any other EVM compatible wallet. So nothing very specific other than asynchronous environment execution. So what does it mean for you as a developer? You have to understand when you send a message from one shard to another, this is a bit more complicated than just call the function. function on same shard. It's a bit more complicated because you have to send it as a special message. And here, a simple example of such a message. It's quite intuitive, and it's shown like sending just event on theory, or sorry, on Solidity. So quite simple. You have some topic, and topic is just depends on what you would like to have, like sending message, sending data, sending whatever you would like to. It's defined by the developers. Target shard ID, so quite intuitive. This is ideal. The target shard you would like to send this message to. Also target address. So this is the address of smart contract on the target shard, and function selector. So who is familiar with Solidity, understand what does it mean. If you're not familiar, you can consider function selector is just quite a kind of API, but function selector used to proper select the function in some smart contract. And you just emit a simple event. So you can see an event like topic, target shard ID, target address, function selector, and definitely arguments you would like to send. So very simple. And you can be sure that this message will be delivered to the target shard. And when it will be delivered, let's define when. So when you send a cross shard message, it can be delivered in two ways, using oracles or routing. With oracles, it's quite simple. So oracles is just, let's say, third party that takes your message, like event, and sends us a special message to a target shard. It's fast and quite simple. But for the verification and like correctness, you use also routing. And routing used like it's shown on the picture, you have some source message shard and target shard. You have intermediate shards connected. So you should understand that if you have, let's say, 1,000 shards, it doesn't mean that every shard will be connected directly to any other shard. It will be some kind of network, like network, like internet, IP network. And they will be connected in some sparse way. So you don't know whether like your target shard will be within 2 shards or 3 shards in distance. But routing allows you to direct your message to a target shard. So like you send a message to a connected shards, and these shards see, okay, if this message is for me or not. If not, they just directed message further. And it goes until it's reached the target. And it will not have such code problem when you send everyone and create such rubbish on the network, because you will have some routing table. So this is like network above the network. And when your message will be delivered, for that reason, we have some global stabilization time. You can imagine this like a time barrier. By that time, we try to synchronize the latest state of the system. So we try to keep all the shards updated with the messages that were sent and signed point of T. And if this T is sent between GST and GST plus 1, we try to guarantee that your message will be delivered at time GST plus 1, at least. So it means that your message will not take much time to reach the target. Yeah, otherwise your network will be like not partition tolerance, but we have partition tolerance network. So let's go with a bit more complicated examples. And this is complicated example with context saving. This is one of the most common patterns in asynchronous execution patterns. If you're familiar with, let's say, JavaScript, you can be familiar with it, or C++. So you can be familiar with such a pattern. So this pattern means that, okay, if you have a request to send the process some data to a destination shard, you will have to receive some reply. And depending on this reply, you would like to whether continue process or stop the process. So how it works? Let's say you have some execute function that just update the counter. And you just go from the top to bottom and follow me. So first of all, you have your counter and save like temporary counter and try to understand, okay, so if update required. So, okay, you update your counter if you have some response. If you require update, you can send a message to a target contract that is located on other shard and actually just respond you with the same message, let's say. For example, here it just send message back to the execution contract. And how this call looks like. So as you remember, you have some topic. You have target ID, you have target address, and you have function selector. Here we see how function selector calculated. This is classic from the Solidity. Yeah, I showed it just to explicitly introduce how it works. So you have your API, get context, and actually you have your source shard ID, source address, and you send this context request. So when this message comes to get context, you just send it back. Your target address becomes 2, target shard ID, topic. So everything is quite simple. You just send it back. And here again, what happens? The message goes again to execute function and goes over again. Okay, you ask when it stops. Yeah, it stops when require update function comes true. Oh, sorry, becomes false. And when the function becomes false, you just admit that, okay, work done, we calculated it. So, okay, I believe that it's quite complicated, but let's have a look at such pipeline. It will be more understandable. So you go from left to right. You have some execution, code execution, and you understand in the code that, okay, cross-shard call needed. You save your context, yeah, what data you would like to save at the moment to restore later. You save this data, invoke the function to call the cross-shard, and stop execution. So your message goes to shard K and invoke target contract that you called from your shard end. So it executes some code and prepare message with the results. So these results invoke your function again, and you continue your function with restore the context that you previously saved. You restore this context, continue execution with the received results, and if you understand that, okay, you need another curl, you need another cross-shard function call to, let's say, shard T, shard F, you go like here, understand the cross-shard call needed, and repeat this again. But you see this important part in the middle that you don't have execution between. So as was said, you stop execution when you save context and create cross-shard call. You should understand that this is just a pattern. This is not just how the protocol will look, but this is how pattern can work for such a system. And with such system, you can achieve arbitrary cross-shard communication calls with feedbacks in fully asynchronous environment in EVM. And here is the final example of ERC20 token transfer. And here example is very simple. Here it's very simple because, as far as you know, ERC20 built around the idea of message sender. In general, message sender is restored using signature that you signed a transaction with. But the uniqueness of the situation that the messages between cross shards is not just a simple transaction. It's a sort of message. And this message restores your context. In this means context like message sender, message value, message balance, etc. Restored as it would be on the source shard. So when you send message to a target shard, the data that you fulfilled will be added with some metadata like message sender, message value, balance, whatever, and sent to target. And it will be restored by virtual machine. So you can be sure that when you send a message from, let's say here, like spender on other shard, so if you would like to spend money on other shard, you just simply create a simple cross-shard transaction. You call transfer, address, and amount, like classic ERC20, and you can see that you don't have message sender in any parameters because it will be saved by protocol, by the person who will create this message for you and send it to target ERC20. And when this transfer function will be called, message sender will be restored from your spender on the other shard. So it's quite tricky, but it allows you to create some sort of solutions that will not differ from the synchronous contract. Yeah, so this is quite simple, by the way, but in general, it allows you to build a lot of applications that, in general, even in synchronous execution, is not very simple, by the way. So, and this is all. Thank you very much. Please, if you have any questions, yeah, I will be glad to answer.
Thank you, Ilya. Thank you for the awesome workshop. And everyone, if you have any questions at all, just drop us a message here and Ilya will be able to answer you. Also, if you feel like speaking using your microphone, just let us know and we'll give that. Okay, I think there's no questions. Oh, there we have one, Ilya, that just popped in the chat now. Mohammed is asking us how to scale up.
So yeah, in general, if you refer to how to scale up the network in general, so as I was mentioned, it's scaling using additional chains. So if you have too many, if you have too high load currently, you can add another chain that will be running in parallel. So like, imagine, let's get back to some, yeah, for example, in here, you have 3 shards. So if you experience high load, permanently high load, there can be added another shard, fourth shard, and it can be just embedded to the whole system. So you can see that you will not have any changes to the protocol itself. Like running a new chain is very simple. So it's just running in new shard, like you just run a new shard from the very beginning, you're allocating new subset of validators, and that's all. So, and you will have a fourth shard, and for example, new users, new applications can be deployed there, to reduce the load on the other shards, or some applications or users can be distributed there. It will be like not mandatory, but it can be done like this. So that's why the scaling is horizontal. You don't need any changes. You don't need any fixes to the existing solution, to the existing code, let's say simple. So you just run a new chain and that's all. Hope I answered. Yeah, we have some hand.
Yeah, thank you for that.
So I will read. So how the tokens are different and how will it affect the migration of current contracts? A shard number have to be included. Yeah, very good question. In general, standard of token will not differ. Yeah, this is one of the important things that we try to keep, to have full compatibility with the Ethereum standards and the Ethereum infrastructure and ecosystem. But yeah, definitely it will require some changes. And let's say simple. So if you have your smart contract, ERC20, let's say, for example, smart contract on Shard1, there will be no changes at all. But okay, you have Shard2, for example. So okay, but the contract is on Shard1. For that reason, used cross-shard communication using some proxies, for example. Proxy is just a skeleton of ERC20 contract. You can call it interface that just redirect requests to Shard1. And as you probably, okay, just a second, I show once again on this example. So you have classic ERC20, and here you have request from the different shard. So you call it as a proxy. So you send a message, and this spender on the other shard contract will be just replaced to ERC20 token dash proxy, for example, and it knows the shard ID the contract is deployed, and it will just send a request to the target contract. That's all. So there will be a very simple situation when you just have a proxy that sends messages for you. But you will see it just an ordinary, let's say, transfer. For you, there will be no difference. You don't experience any changes. So something like an internal routing, common place rather than specific shard. Yeah, so yeah, this is a draft example. Yeah, in general, it's possible to have some internal routing, but it's yet not understandable if the system will be static or dynamic. We are working currently on that. If the system will be dynamic, it will be a bit more complicated to handle. For the shard, for the static system, so static means like when you have predefined number of shards, and in general in that system, yeah, quite likely that will be hidden behind the protocol logic. Yeah, you won't need. This is just example. Yeah, you have to understand that examples of these smart contracts is just examples. This is not like it will look like finally. This is to explicitly show how it will look like in general. Is there a way is there a way for me to get a copy of the presentation? I believe Orbi maybe will share later in Twitter, or I don't know.
Yeah, the presentation is being recorded and we're gonna upload it onto our Discord, the educational channel. So you guys will be able to have the presentation and everything over there very soon. Are there any more questions? If there aren't any, we'll be closing it off here. Thank you, Ilya, for the wonderful workshop presentation. And thank you everyone for participating up until now.
Yeah, so yeah, thank you very much. Yeah, if you will have any like technical questions and you would like to know more some technical details, you can reach me in Discord or Twitter. So just direct the question to me and we'll try to answer it.
Awesome. Thank you everyone for participating. We'll hopefully see you in the next one as well. Have a great day over there.